Thank you very much. Our next speaker is May Azzawi from the Manchester Metropolitan University in the UK.
Okay. Good afternoon, everybody. I'm May Azzawi, and I'm going to be presenting to you work from my lab at the Healthcare Science Research Institute at Manchester Metropolitan University in the United Kingdom. We're an interdisciplinary research group with a specific interest in vascular function studies and how nanoparticles affect vascular function. So we are interested firstly in the biocompatibility of the nanoparticles, and secondly in how nanoparticles could be used for the restoration of vascular function. So one type of nanoparticles that we're particularly interested in is the silica nanoparticle, because silica nanoparticles have potential for imaging, diagnostics, and the treatment of disease, because they can be dye-doped and they can be functionalized and surface targeting. They are stable under fluid shear stress. When nanoparticles are injected into the bloodstream for purposes of imaging diagnostics, for example, the endothelial cells that line the blood vessels are the first cells to be exposed to the nanoparticles. The endothelial cells are very important in the maintenance of blood vessel diameter and the regulation of blood vessel diameter through the elaboration of a number of mediators, including nitric oxide, and also in the maintenance of the health of the vessel and the prevention of events that lead to atherosclerosis. So this is a normally neglected part when individuals look at the effects of nanoparticles in vivo. So our previous studies have demonstrated that when we incubate silica nanoparticles in ex vivo, in isolated aortic vessels, we can show that for those that are less than 100 nanometers in diameter, they attenuate endothelial-dependent dilator function. We can show that they are rapidly taken up by the endothelial cells within 30 minutes. If we co-incubate in superoxide dismutase, we can show restoration of function, suggesting that the reactive oxygen species generated, reactive oxygen species generated by the silica nanoparticles can quench nitric oxide that is released by the blood vessel, and therefore attenuation the dilation. Silica nanoparticles can be coated so that they are more biocompatible, and we're specifically interested in Syria because of the radical scavenging property. So our key question was whether Syria coating of the silica nanoparticles would prevent the silica nanoparticle-induced attenuation of vasodilation and hence make them more biocompatible. So we fabricated silica nanoparticles of 50 nanometers in diameter, and we coated these in the Syria nanoparticles. We finally characterized these using DLS and using the EDAX for elemental analysis. When we looked at the effect of the silica nanoparticles on vasodilator function, that is the endothelial-dependent acetylcholine responses, we show there's a significant attenuation in dilation. However, when we incubate in the Syria-coated silica nanoparticles, there's a significant improvement. And we can show that these nanoparticles are rapidly taken up into endosomal structures within the cytoplasm of the endothelial cells. So finally, these results will inform the future fabrication of silica nanoparticles with increased biocompatibility. Syria-coated silica nanoparticles can represent a novel therapeutic tool. We're very keen to collaborate, especially in relation to the Horizon 2020. We have expertise in vascular function studies, and we also have an ex vivo model that allows us to examine vascular function under conditions that mimic the physiological state of pressure and flow. you're welcome to our poster number 5, for further discussion. Thank you very much.
Thank you very much. Our next